Okay, picture this. You live in a pretty nice apartment building. You pay your rent on time, you follow all the rules, but the person living right next door decides to throw a loud, wall-rattling party every single night. You can't sleep, you can't focus, and honestly, your quality of life just totally plummets.
Well, let's dive right into this explainer, because in multi-tenant software systems, this exact same nightmare happens literally all the time. But, instead of your neighbor blasting loud music at 2 a.m., they're hogging CPU cycles, or disk I/O, or network bandwidth. It completely steals your peace, quiet, and overall system performance. So, welcome. Today we're going to unpack a really fundamental flaw in modern architecture.
We call this the noisy neighbor problem. The formal definition here is that it occurs when one tenant, process, or workload just consumes a completely disproportionate share of a resource, and that actively degrades the performance for everyone else sharing that exact same space. The absolutely crucial word to focus on here is shared. Fundamentally, this is a failure of resource contention and isolation. So, here's our roadmap for today. We'll start by examining the core problem, map out exactly where this noise happens in the stack, talk about the real dangers of shared systems, figure out how to design for quiet, and finally wrap up with some real-world architectural solutions. Let's get to it.
All right, part 1, the noisy neighbor problem. Let's see exactly where this architectural flaw likes to hide.
Like I mentioned, this headache only exists because of resource sharing. Just like sharing walls in an apartment building, in infrastructure, we share components to save money and boost efficiency, right? So you might have virtual machines on the same physical host competing for CPU cores, or pods on the same Kubernetes node. Heck, it could be tables in the exact same database, or even application threads in the same process pool. The bottom line here is simple. If you are sharing it, somebody else can hog it. Which brings us right to part 2, where the noise happens. Let's break down the technology layer cake.
Now, what's really fascinating here is how thoroughly this contention sneaks into literally every single layer. Just look at the breakdown. Down at the compute layer, a container without CPU limits can easily hog all the cores on a node. Over in storage, heavy sequential writes can just completely starve everyone else's IOPS. Moving up to network, a single massive traffic spike can saturate a shared network interface or load balancer. It keeps going through databases and caches where, long-running analytical queries will exhaust your connection pools or massive keys evict your cached data. And it goes all the way up to the app thread layer, where a slow downstream dependency can consume every last one of your worker threads. It is truly everywhere.
So, moving into part 3, the danger of shared systems. Why is this so absolutely critical to fix? You know what the absolute worst part about the noisy neighbor problem is? It's completely non-deterministic. It shatters the core assumption of performance isolation, which directly threatens your SLAs. Just think about the sheer pain of troubleshooting this. Your code might be flawless, your service is totally healthy, but your application is still degrading and throwing errors simply because of what some other random tenant is doing on the same server. It's maddening. And man, it rarely stops with just one slow process. A full system crash can unfold so fast here. First, the resource hog starves the system. Second, because the system is starved, other completely innocent tenants start timing out. Third, and this is the killer, those tenants automatically retry their requests. Suddenly, boom, you have a thundering herd. It's a massive wave of retries hitting an already overloaded system, causing a cascading failure that will bring your entire platform right to its knees. Okay, take a breath. We can prevent this. Let's look at part 4, designing for quiet, and open up the architect's tool belt. We actually have a whole set of mitigation strategies to enforce some strict apartment rules. We can build physical walls with resource isolation or put hard caps on usage using rate limiting and throttling. To keep things balanced, fair scheduling and auto-scaling make sure everyone gets a turn and spikes are absorbed. We can also use workload separation to keep heavy background tasks far away from quick, real-time paths. And obviously, absolutely none of this works without strict per-tenant monitoring to actually spot the noise when it happens. So the crucial point we really have to nail down is the trade-off between cost and isolation. On the heavy, highly secure side, we've got hard multi-tenancy. This means dedicating entirely separate VMs, clusters, or databases to each tenant. It gives you the highest possible isolation, but wow, look at the cost. On the lighter, more balanced side, there's soft multi-tenancy. You share resources, but you use control groups or namespaces to enforce the limits. It's way cheaper, for sure, but you are relying entirely on your software boundaries to keep those neighbors quiet. One of my absolute favorite ways to enforce these boundaries is the bulkhead pattern. This is a concept brilliantly detailed in Michael Nygaard's book, Release It. Think of a submarine or a big ship divided into watertight compartments. If one compartment floods, the bulkhead doors seal shut and the ship stays afloat, right? In our infrastructure, we do this by partitioning resources, like connection pools or thread pools, per tenant or per dependency. So if one tenant's requests bottleneck, they only flood their specific compartment. The rest of the system just sails on smoothly.
Let's rapid fire through some tactical ways to actually pull this off. You can drop token or leaky bucket rate limits right at your API gateway, basically putting a strict volume limit on that neighbor's stereo. You can build in back pressure so an overloaded service actively tells upstream callers, hey, slow down, instead of just silently dying. You can use CPU schedulers with fair share queuing. For databases, physically separate your heavy analytical OLAP workloads from your fast transactional OLTP replicas. And please, absolutely rely on per-tenant metrics, because if you only monitor your aggregate traffic, you are never going to figure out which tenant is actually causing the spike.
Finally, we hit Part 5, Real-World Architecture Solutions. We've talked a lot of theory, but how does this play out in reality?
Now, you might be wondering, okay, but how do the massive tech giants actually handle this? Because let's be real, these aren't just academic theories. These are the industry standards used by the largest platforms on Earth to maintain order and hit their SLAs. Well, just look at our foundational cloud providers and orchestrators. It's genuinely impressive how they engineer around this stuff. AWS EC2 uses CPU credits for their burstable instances to cap runaway usage. And their proprietary Nitro hypervisor, it's specifically designed to minimize the noisy neighbor tax compared to older virtualization tech. Kubernetes natively provides resource quotas and limit ranges. These are built directly into the orchestrator so you can mathematically prevent one pod or namespace from starving others on a shared node. And this brilliantly illustrates how software limits protect the broader ecosystem. Managed databases like Amazon RDS or DynamoDB use provisioned IOPS and throughput capacity, guaranteeing you disk performance no matter what other workloads are doing. Netflix famously popularized the bulkhead pattern and circuit breakers using Hystrix to stop thread pool exhaustion from cascading across all their microservices. And massive SaaS platforms like Salesforce, they actually bake per-tenant governor limits directly into their platform. They cap API calls, query rows, and CPU time so no single customer's custom code can ruin the experience for everyone else. So as we wrap up this explainer, if you only take away one thing, make it this. The noisy neighbor problem isn't something you can just fix with a single neat trick or a quick patch. It is something you must actively design against at every single layer of your stack. You have to isolate resources, enforce limits, schedule fairly, and crucially, you've got to monitor per tenant, not just an aggregate. I want to leave you with this really profound architectural principle from our source material. Anywhere you share infrastructure to save cost, you're trading away some isolation. It's just a fact. Sharing lowers your bill, but it fundamentally opens the door to contention. Which leaves us with the ultimate question. Take a look at your own system designs right now. Are you making that trade-off consciously, with proper limits and bulkheads already in place? Or are you making it by accident, just waiting around for a noisy neighbor to move in and completely crash your party? Thank you so much for joining me for this explainer. I really hope this helps you build quieter, much more resilient system.